All right, welcome back. I'm the Tutor Wizard. This is Willa. What we're going to do is another linear algebra, lecture 5. We're going to do some determinant properties, and then we're going to do Kramer's rule and show why we want all of the inverse matrices and determinants, all of this machinery. Basically, we want to solve linear n by n systems is what we're going to do with all of this, correct? Good. All right, so first of all, let's recall we're going to do some determinant properties, and then we're going to show how to use those properties to efficiently compute inverses and use determinants to solve linear systems. Let's compute a couple of determinants first. The determinant of A is equal to the determinant 1 of 3, 1, 4, negative 2, which is equal to 3 times negative 2 minus 1 times 4, which is negative 6 minus 4, which is negative 10, which is not 0, so this matrix is invertible. The other one, this is going to be horrible, but let's see where we go with this. What do we have? Basically 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I threw on a couple of negatives. Let's look at the determinant of that. The determinant of B is equal to the determinant of 1, 2, 3, this is a 2, where are you going? Negative 4, 5, 6, 7, negative 8, 9. The reason I'm picking this matrix to compute 1, 2, 3, 4, 5, 6, 7, 8, 9 is because the numbers are going to get horrible, and by doing it by definition or doing it without knowing how to use these determinant properties, this can take an extremely long time. We're going to get a bunch of horrible numbers. So this is not in general the way that we're going to want to do this. This is motivation, hopefully, for why you want to learn these determinant properties and make the computation of determinants more efficient. Let's cofactor expand along the first row. The determinant of A is A11 C11 plus A12 C12 plus A13 C13. This is equal to 1 times C11, which is equal to M11, which is the determinant obtained by blocking off row 1 and column 1, which is 5, 6, negative 8, 9, minus 2 A12 times M12, then minuses for the cofactor, and then I block off row 1 and column 2, so negative 4, 6, 7, 9, and then plus A13, which is 3 times C13, which is equal to M13, which is obtained by blocking off row 1 and column 1, so negative 4, 5, 7, negative 8. This is the determinant. Now I compute 3 2 by 2 determinants because I didn't have any zero coefficients or we didn't do any determinant properties. Now I have to compute all of those numbers. This is equal to 1 times 45 minus plus 48 minus 2 times negative 36 minus 42 plus 3 times 32 minus 35, which is equal to 48 plus 45, you're going to get 13, 1, you get 93. 93 minus 2 times, I've got 42 plus 36 is 8 is 78. 2 times 78, and then we're going to times 2, we're going to get 16, we're going to get 156 is what we're going to get, and then plus 3 times, what did I get? Negative 3. So this is 93 minus 9 minus 156, which is 156 plus 9 is 15, and then we're going to get 165 minus 93, which is, we're going to get 216 is 72. This is equal to 1 times C11, which is cofactor expansion along top row, so we're going to get 5, 6, negative 8, 9, and then minus 2 times negative 4, 6, 7, 9, plus 3 times negative 4, 5, 7, negative 8, which is equal to 1 times 45 plus 48 minus 2 times negative 36 minus 42, and then plus 3 times 32 minus 35. This is equal to 1 times 93 plus 2 times 42, 36 is 8, 78. 78 times 2 is 16, 156 is 156, so plus 156 minus 9, so I get 156 plus 93, which is 9, 14, 249 minus 9, which is 0, 240, so this is equal to 240. I got it this time. I had a plus error in the first time I tried this. We'll put it at the end of the video so you can see I made a mistake, but 240 is the determinant. Again, why have I done this? Because when we have all non-zero numbers and we use even cofactor expansion or we use the definition, then it takes us a long time to compute and we have a long high probability of getting errors. So we want to use determinant properties so that we can speed this up. The first thing that we want to show you is quick ways of determining whether a determinant is 0 or not. Let A be an n by n matrix. 1, if A has an entire row or column of zeros, then the determinant of A is 0. If you cofactor expand along that column, you'll get 0 times 0 times 0 times, and then it will be 0, is essentially the proof. And then 2, the determinant of A transpose is equal to the determinant of A. Quickly again, how can this work? If I cofactor expand along column 1 in this one, then transpose just means I've cofactor expanded along row 1. That computation will be the same. They're going to be equal to each other. So transposing doesn't change the determinant. You could transpose it. It won't make a difference. The calculation will be the same. And if you have a row of zeros or a column of zeros, you don't have to think about this or cofactor expand anymore. You just know that you have the determinant 0. This is the first thing we want you to see. Theorem. Let A be upper triangular or lower triangular or both, which is diagonal. Then, remember, we always create upper triangular when we go to REF, and that's exactly what a version of what we're going to try and do. Some of the techniques are trying to say, do this, get yourself to upper triangular, and then you can use this theorem every time. But getting to upper triangular takes a few more steps in row reduction, so I'm going to do something in combination of trying to do a little bit of this and cofactor expansion. Then, what does this tell us? If you have an upper triangular, so if you have a matrix which has just information here and then zeros below, or it says if you have lower triangular where now I have the information in the lower triangle and I have zeros above, or if I have both of those scenarios where I just have diagonal entries, then the determinant of A is equal to A11 times A22 times ANN. The determinant is the product of the diagonal entries if the matrix is upper or lower triangular or diagonal. Let's do a quick example of that to show you exactly what they mean by this in the theorem. Let's do it right below. Let A equal 1, 2, 3, 0, 1, 4, 2, 3, negative 7. That's not what I wanted. Let's do this. The other one we would have to change using the properties. So I check, it is upper triangular. And what that says is, it claims that the determinant is just equal to A11, A22, A33, which is equal to 1 times 7. So the determinant is 7. Why is that? Let's do it by cofactor expansion just to see, just in case. This is going to be, what is this? If I cofactor expand along this column, which is what we're going to do eventually, I have this will be equal, this says the determinant of 1, 2, 3, 0, 1, 4, 0, 0, negative 7. Oh, there's a negative there, so the determinant was negative 7. Sorry, 1 times negative 7. What is this? This is equal to cofactor expansion along this, and this will give me 1 times 1, 4, 0, negative 7 times minus 0 times I don't care, plus 0 times I don't care. Those are gone. And what do I get? Now this is determinant this minus this, so 1 times negative 7, which is negative 7. The determinant is negative 7. So this is why, essentially, this is the idea of the proof. When you have a big one, you just keep cofactor expanding along this column, and you'll get down to where you get the product of all of the diagonal entries. Now what we're going to do is list the 3 determinant operations. One of them is extremely useful for me, and it doesn't change the determinant at all. That's going to be number 3, and so that's the one we're going to want to use the most. Number 1 and number 2, try to avoid using them at all if possible, but we're going to list them for completeness sake here. The first one is, and let me write them all out in what they say first, and then I'll explain what's going on. We'll do an example. I'll show you in the 2x2 case. What it says is, if B is obtained from A, let A be an n by n matrix. If B is obtained by A by multiplying a single row or column, I would stick to row operations right now. So far you've been trained in row operations, but you can do it to columns now. This is not solving systems, this is computing a number algebraically with the determinant. So if we multiply a single row or a single column by k, then the determinant, let's write it like this, then the determinant of B is equal to k times the determinant of A. This one's dangerous. What this says is, I'll show you exactly what's happening here. I have this matrix and I want to compute the determinant, and for some reason I want to get this a leading 1 because that's what I've been trained to do. Or if we make this more complicated, let's try that again. If I have this matrix and I want to get a leading 1, I might think, let's multiply by 1/2, and that's not what's going to happen anymore. We're not multiplying both sides of an equation by 1/2 to cancel this anymore. What you have to do is see this as, if this is A or this is B, then what they're saying is you need to factor the k out of this. So what we're going to write this as, we're going to write this, you're like, there's not a 2 here. Yes, there is. We write 2 over 2. And now I can write this as 2 times 1 times 3 over 2 times 2. And 2 times 2 is that first row, 3, 1, 2, 17, 9, 7. And that tells me that I can factor the 2 out. 2 times 1, 3 over 2, 2, 3, 1, 2, 17, 9, 7. So then if I'm computing the determinant, it says if B is obtained from A by multiplying by, or this is B, is obtained from A by multiplying by a row by 2, then the determinant will be multiplied by that value. Don't use them if you don't have to. But you don't multiply on both sides anymore. You factor the number out of the row is how you do determinants. Condition 2. This one's also not so bad. It's talking about interchanging rows or interchanging columns. If B is obtained from A by interchanging 2 rows or 2 columns, then the determinant of B is negative the determinant of A. Even when we do cross product of U cross V is I, J, K, U1, U2, U3, V1, V2, V3. And people ask, well, what if I put V in there and what happens to that? Well, now you see this is a determinant. If I interchange those 2 rows, this will be equal to negative I, J, K, V1, V2, V3, U1, U2, U3, which is what? This is negative V cross U. So U cross V is negative V cross U. What the determinant property is now saying is I was allowed to make that move because if I interchange 2 rows or 2 columns every time I do it, I get a negative on the outside of the determinant. That's property 2. Again, don't try to use number 1 or number 2. Number 2 is fairly safe. Every time you do that, you get a negative on the outside. Number 3 is the one we're going to use the best because it doesn't change the determinant at all. Determinant property 3 is if B is obtained from A by replacing a row, again, or column, but I would stick to row operations because that's what you know right now. By replacing a row Ri by Ri plus K times Rj, a multiple of another row, similar to the row operation ones. This doesn't change the determinant at all. Then the determinant of B is equal to the determinant of A. And this is how we eliminate and get zeros in columns. So this is the row operation that we're going to use. If I have 1, 1, negative 1, 0, 2, 3, 4, 8, 9, what I want to do is get rid of these spots so I can cofactor expand and make those zeros. Now what it's saying is I'm allowed to replace these rows by multiples of the first row and I won't change the determinant at all. Let's prove these in the 2 by 2 case. So if A is A, B, C, D in the 2 by 2 case, then what does property 1 say? B is going to be what? It says obtained from A by multiplying a row, no, number 1, yes, multiplying a row by a single row or a single column by a constant. So in this case, we have 4 choices. We could multiply row 1 by K, or row 2 by K, or column 1 and column 2. Let's do row 1 and column 2. So let's say B is obtained from A by multiplying row 1 by K. So we're going to have KA1 and KB, and then we have C and B, C and D. So this is the matrix B, which was obtained from A by multiplying row 1 of A by a number K, which is not 0. Then, this says, what is the, and here, what do we know? The determinant of A is going to be AD minus BC. The determinant of B is equal to KA, KB, CD, which is equal to KA times D minus KB times C. There's a K in both terms. I can factor that out. That's K, AD minus BC. What is this? The determinant of A. If I multiply a column, what if B is obtained by multiplying column 2 by K? Then I would have AC and KB and KD. Well, that says the determinant of B is equal to A times KD minus KB times C, which is equal to K AD minus BC, which is K times the determinant of A. So if you multiply a row or a column by a constant, the determinant is K times that number. Coincidentally, what does that say? K, the determinant of K A to the n by n is. Scalar multiplication multiplies every row by K, and there's n rows, so that will be equal to not just K times the determinant of A, but it'll be K to the n. 2, what if I interchange 2 rows or 2 columns? Well, in this case, there's only 2 cases, so let's interchange the 2 rows, C, D, A, B. Then that says the determinant of B is going to equal CB minus AD, which is equal to negative AD minus BC, which is negative the determinant of A. What if I interchange the 2 columns? Then B would be BDAC. That says the determinant of B will equal B times C minus A times D, which is negative AD minus BC, which is negative the determinant of A. And for the final property, this is the magical one to show you that it actually doesn't change it at all. If B is equal to, let's do the row 1. So we're going to replace row 1 with K, row 1 plus K times row 2. What does that look like? I'm going to get A plus K times C, and then I'm going to get B plus K times D, and then I'm going to have CD. This is B, which has been obtained from A by replacing row 1 of A by row 1 plus K times row 2. This says the determinant of B is equal to A plus KC, B plus KD, CD, which is equal to A plus KC times D minus B plus KD times C, which is equal to AD plus KCD minus BC minus KCD. These cancel magically, and we get what? AD minus BC, which is the determinant of A. It didn't change. This is the operation we're going to use the most, and it doesn't change anything. Good. What I'm going to do is give you my fastest method for computing determinants. What we're going to use is a combination of those 3 determinant properties and now cofactor expansion to get a leading one in the top left corner. Eliminate below by using the safest row operation, which is replacing these rows by multiples of row 1, which won't change the determinant at all. Then I'm going to cofactor expand along the first column, and that will give me a Matryoshka doll of determinants, and we're only going to have to compute 1 of each size, and then we get down to 2 by 2, and that's where we compute our determinant. The determinant of, for the first one, the determinant of A is equal to the determinant of 0, 3, 1, 1, 1, 2, 3, 2, 4. Now what I'm going to use is a combination of cofactor expansion and the determinant operations. What I want is I want to get a leading one in the top left corner and then eliminate below and then cofactor expand along this column. What I see is I do have a leading one. I'm going to interchange those. Anytime I interchange 2 rows or 2 columns, I get a negative. So I'm going to interchange those, and I get 0, 3, 1, 3, 2, 4. Now what I'm going to do is the safe operation that we're allowed to do is I can replace row 3 with row 3 minus 3 row 1, and that won't change the determinant at all. So I'm going to do that now. That's negative 1 times this negative times, what am I going to do? 1, 1, 2, 0, 3, 1. And now 3 minus 3 is 0. 2 minus 3 is minus 1, and 4 minus 6 is negative 2. Now what I want to do is cofactor expand along this column because these coefficients are 0. It doesn't matter. I don't have to compute the cofactor C21 or C31. Therefore, this is equal to negative 1 times from the interchange of the 2 rows times 1, which is A11, times C11, which is 3, 1, negative 1, negative 2, times I don't care, these ones are 0. And that gives me negative 1 times, what do I get? Negative 6 plus 1, which is equal to what? Negative 1 times negative 5, which is 5. The determinant is 5 this time. For the bigger one, what are we going to get? For the second one, the determinant of A, I have a leading 1. And what I want to do again is I want to use Matryoshka dolls. I want to get cofactor expansion along this column and then get 1 3 by 3 and then get a leading 1, and then cofactor expand along this column and get 1 2 by 2, and then we have our determinant. How am I going to do that? I have to do the safest thing again we can do is I have 3 determinant row operations I can change, and it won't change the determinant at all. So I'm going to get rid of the 5 and the -1 and the 2. So this is equal to, and it will not change it at all. 1, -2, 3, 1. First of all, I'm multiplying by -5. So I'm going to get 5 minus 5 is 0. -9 plus 10 is 1. 6 minus 15 is -9. And 3 minus 5 is -2. Now I'm going to add them. -1 plus 1 is 0. 2 minus 2 is 0. -6 plus 3 is -3. -2 plus 1 is -1. Now I'm going to multiply by -2. 2 plus -2 is 0. 8 plus 4 is 12. 6 minus 6 is 0. 1 minus 2 is -1. Why have I done that? Because now I can cofactor expand along this column, and I don't have to compute C21 or C31 or C41. I don't care, because it's going to be multiplied by 0. Technically what this is this. A11 C11 plus A12 C12 plus A13 C13 plus A... No. Cautiously training me to do row 1, but I'm doing column 1. This is plus A21 C21 plus A31 C31 plus A41 C41. But A21 is 0, and so is this, and so is this, and that's why we've done that. And hopefully now you can see that's what I'm doing. In my mind, I can see this is cofactor expansion along this column, but those are going to be zeros. So I don't care, I don't care, I don't care. I'm not computing those. Now that you can see that, every time we do that, it's always the same, because the strategy is always the same. I don't need those other terms. So the determinant now is A11 times C11. C11 is always the positive M11, which is the minor obtained by blocking off row 1 and column 1. This is C11, which equals M11. This is A11. And all the other ones are zeros. So using that technique by cofactor expansion, this is equal to 1 times the cofactor, which is 1 minus 9, -2, 0, -3, -1, 12, 0, -1. And now you can finally see, because I've done a 4 by 4, now forget where that came from. I now have to compute a 3 by 3 determinant. So ignore that. Keep your numbers that you've used from the operations out front, if you have any. This is a 1, so I can get rid of it. And now what am I going to do? I need to find the determinant of this 3 by 3 one. I'm going to do the same thing. I've got a leading 1. I'm going to get rid of this, and then we're going to do cofactor expansion along column 1 again. What do I have to do? This is equal to, I can change row 3 to row 3 minus 12, row 1, and it doesn't change it. So this will equal 1, -9, -2, 0, -3, -1. Now I'm multiplying by -12. 12 minus 12 is 0. 0. 9 times 12 is 108. Negative. And -1 plus 24 is 23. There we go. The universe doesn't care how big the numbers are. Now I'm going to cofactor expand, and there's the Matryoshka doll. There's the 2 by 2 I need. Now this is, again, A11 times C11. This is C11. This is A11. I'm doing the same trick, except now it's a 3 by 3. This will be equal to, again, A11 C11 from this matrix, which will be, again, 1. It's usually going to be a 1, because I like to get a leading 1. So the A11 is always going to be a 1 for me. It could be the non-zero entry. And then now what is this? This is the 2 by 2 determinant, -3, -1, 108, 23, which is equal to -3 times 23 plus 108. 69. This is 108 minus 69, which is 39. 3 times 13. Determinants, Matryoshka dolls. I use the properties. I get a leading entry. I kill below. Then I cofactor expand along column 1. 1 3 by 3 determinant I have to compute. And then I get the same thing. I get a leading one, I kill below if I have to. And then I cofactor expand along, and then and then there's a little tiny one inside, and the little tiny ones are the cutest ones, and they're the ones that compute AD minus BC. That's how I compute the determinant of 39. Let A and B be n by n matrices. 1. A minus 1 exists. So A is invertible if and only if the determinant of A is not 0. 2. The determinant of A times B. Again, we have to use a bunch of elementary matrices, and this takes a lot of work to actually prove this, but magically it is true, is the determinant of A times the determinant of B. I also stated it earlier, but I'll list it as a property right now. In property 1 of determinant properties, if I obtained B from A by multiplying any row or single row or column by a multiple K, then it's K times the determinant. So now if I'm an n by n matrix and I scalar multiply A by K, what's the determinant of that? The determinant of K times A, which is n by n. Is it just this? Can you just pull it out? Determinant is not a linear operator transformation because it operates as K to the n. Each row, A has n rows, and scalar multiplication goes into each row. So I have to pull K out n times, and that will be the determinant, applying the properties. And then for if A minus 1 exists, then the determinant of A minus 1 is equal to 1 over the determinant of A. This is kind of magical. Remember, in numbers, this is a real number. And that's the multiplicative reciprocal of the number determinant. And so it says the determinant of the multiplicative inverse of a matrix is the multiplicative inverse of the determinant of the original matrix. Properties. What we're going to do now is we're going to actually apply this machinery of determinants and inverses to solving linear systems. Okay, so to finish off this video, what we're going to do is we have the machinery of determinant, we have the machinery of inverses, we know how they're related to each other, and now we're going to use those in 2 different ways to solve linear systems back to square one. I wanted all of this machinery and cutting down. I tell you to go cut trees in the forest, and everyone's so proud at first really because they became a lumberjack, and you're like, I can cut down trees, look at all the trees I cut down. It's like, yeah, but I didn't just want to cut down trees, I wanted to build a log cabin and something more sophisticated from that. Now that we have all that and we've felled all the trees we need and we have all the moving parts, now let's see how we solve a linear system. The first way, and then we'll do Kramer's rule, which also gives us another way of solving linear systems. You'll have more than enough rope to hang yourself. Just be careful. What we're going to do now, and this is where we got matrix multiplication from, remember, we're viewing this system as a coefficient matrix, which is n by n. Matrix multiplied by a vector x, which is actually an n by 1 matrix, and that equals an n by 1 matrix also. What we want to do with that is, if the determinant of A is not 0, we're going to check if and only if A minus 1 exists. Once I know that, and I've checked that the determinant is non-zero, we can multiply both sides. It's the same thing as what we're doing in the 1 by 1 case. X equals B. As long as A doesn't equal 0, which is the determinant, I know A minus 1 is just 1 over A. And what do we do with that? We multiply on both sides by A minus 1. I get A minus 1 times A, I associate, equals A minus 1B. A times A minus 1 is 1 times X, which is A minus B. And then we get 1 times X doesn't do anything, and I get X is A minus B, which we normally write as B over A. I'm going to do now this exact same thing with this machinery. I now have matrix multiplication. I have checked that the determinant is not 0, so I have the multiplicative inverse of A. We're going to multiply both sides by this A minus 1, but now it has to be on the left. always on the left. This will be, if and only if I can associate this, this will be A inverse A times X equals A inverse B. What does that do? These guys give me the identity matrix. In times X equals A inverse B. What does that do? Nothing. So I get X is A inverse B. This is what we want to do with this machinery. Let's do that for a 2x2 system, and I'll show you how it works. I'll do 2x2 systems for both this method and the Kramer's rule, just because finding the inverses of 2x2 is fairly fast, so pedagogically I can explain how the method works. It doesn't really change, it just is more computation when we get larger matrices. Example. Solve the linear 2x2 system. 2x1 plus 3x2 equals 1 and 5x1 plus 7x2 equals 2. And then we'll force you on the exam, I'll say using a minus 1 if it exists. What are they saying? They're saying I have A is 2, 3, 5, 7 is the coefficient matrix of this system. The augmented matrix is actually equal to 1, 2. So we could use row reduction. We have that method. Now what we're doing instead is saying this. A is equal to 2, 3, 5, 7. So the inverse A minus 1 is equal to 1 over the determinant of A times the adjoint of A, which is equal to 1 over negative 1. We've computed this for 14 minus 15 is negative 1. And then what do I get? The adjoint, which is 7, 2, negative 3, negative 5. And so A minus 1 is equal to negative 7, 3, 5, negative 2. Now I have the inverse, and we worked so hard to do that, and there's all the machinery I was just talking about. What am I going to actually do with that? I'm now going to solve my system this way. What does it say? The unique solution to the linear 2x2 system is x, which is x1, x2 is equal to A inverse B, which is equal to A inverse is negative 7, 3, 5, negative 2 times 1, 2, the vector B. And now that is equal to a 2x2 matrix times a 2x2 matrix, 2x1 matrix. The inside indices match and the size will be 2x1 again. And I'm going to get what? Negative 7 plus 6 is negative 1, and 5 plus minus 4 is 1. This is the unique solution. Just to check, let's do that the old-fashioned way of row reduction. 2, 3, 5, 7, 1, 2. This is equal to, I'm going to do 5 minus 4 is going to give me 2, 3, 1. 5 minus 4 is 1. 7 minus 6 is 1. 2 minus 2 is 0. Then what am I going to do? I'm going to interchange those. So I'm going to get 1, 1, 0. And then I'm going to do 2 minus 2 is 0. 3 minus 2 is 1. And 1 minus is 1. So what does that tell me? I'm in REF now. That tells me that x2 is 1. And x1 is negative x2, which is negative 1. I did get the unique solution, negative 1, 1. Negative 1, 1. This says x1 is negative 1 and x2 is 1. The unique solution to the system. So finally, that machinery has given us another way of solving the linear n by n system. Now for Kramer's rule, I'll state the theorem. I'm going to define something weird again in there. We're going to make these matrices AI, where I replace column I with the equals vector or the solution vector B from the right-hand side of the equation. Theorem. Let A11 x1 plus dot 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 plus A1n xn equal B1 to an1 x1 plus dot 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 plus ann xn equals bn. Be a linear n by n system. And let A equal A11 to A1n dot 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 an1 to ann be the coefficient matrix, and B equals B1 to Bn with the determinant of A not 0, so I know the inverse exists, but more importantly here I need to divide by the determinant to compute these. Then the unique solution is given by, to the linear system, is given by x1 equals the determinant of A1 over the determinant of A. Xi is equal to the determinant of AI over the determinant of A. And then all the way to xn, all of our n solutions, xn is going to be the determinant of an over the determinant of A. What that says is the unique solution is the ratio of determinants. So it says in general you should have fractions unless the determinant, if all of these determinants are divisible by these determinants, you won't get fractions. Otherwise you should have fractions. Also, what are these guys? Where AI equals A1 dot 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 AI minus 1 B AI plus 1 AN, where AI is the matrix obtained from A by replacing column I with this matrix, or this column vector B. And so first what I do is I take the coefficients matrix A, I compute the determinant. If that's not 0, I know I can do this business of Kramer's rule. And the unique solution is obtained by, first I compute the determinant, which I already computed. Then I have to compute n more determinants, A1, AN, and I have to replace all the columns one at a time with this guy, B, and then find those determinants and then compute the ratios of these, and those are the unique solution. This is called Kramer's rule, after Gabriel Kramer. Let's do an example. We use the same system we just used in the last one, and we did the two other ways, and we'll see that this third way, or Kramer's rule, will actually compute the same thing as well. Example: solve 2x1 plus 3x2 equals 1 and 5x1 plus 7x2 equals 2 using Kramer's rule, or the ratio of determinants. All right. A is equal to 2, 3, 5, 7. A1, I'm going to compute all the A's first. A1 is obtained from A. The B, first of all, is equal to 1, 2. Now from those two scenarios, A1, I replace column 1 of A with this vector, 1, 2, and then 3, 7. And then A2 is going to be, I leave the first column alone, and then I replace the second column with this vector, 1, 2. Now that I have those, I have to compute the determinants. The determinant of A, I should always check first even before I construct those. But the determinant of A we already did is 2 times 7 minus 3 times 5, which is 14 minus 15, which is negative 1, which is not 0. Therefore, Kramer's rule applies, and we can make these ratios of the determinant of A1 over the determinant of A, determinant of A2 over the determinant of A. The determinant of A1 is equal to the determinant of 1, 3, 2, 7, which is equal to what? 7 minus 6, which is 1. And the determinant of A2 is equal to the determinant of 2, 1, 5, 2, which is equal to 4 minus 5, which is negative 1. What does that tell me? This tells me the unique solution is given by x1 equals the determinant of a1 over the determinant of a, which is equal to 1 over negative 1, which equals negative 1, and the x2 is equal to the determinant of a2 over the determinant of a, which is 1 over 1, which is 1. And this is exactly what we found. The unique solution is negative 1 and 1. This is Kramer's rule. Please subscribe below, hit the notification bell for other videos. I will see you soon, and hit this button right here to subscribe, please.